learner. I am Ajay Kumar, Assistant Professor, Department of Computer Science and Informatics, Central University of Himachal Pradesh. Today we will study about the method of recurrence solving in Block 1, Unit 1. So, these are the methods for solving the recurrences. First is substitution method, second is iteration method, third is recursion tree method, and fourth is master method. So, if any recursion is given according to the situation, we can use these methods for solving that recurrences. So, first we have to understand what is the meaning of recurrence relation. So, recurrence relation is a mathematical model that captures the underlying time complexity of an algorithm. Okay. So, in every relation, in every recurrence relation, there will be the mathematical modeling. So, for what mathematical modeling is required? To capture the time complexity of an algorithm. So, to solve the recurrence relation means to obtain a function obtained on natural number that satisfy the recurrences. We will see that things in example. Like for example, the recurrence describe the worst case running time Tn of a merge sort procedure, that is Tn equal to theta of 1 if n equal to 1, and that is 2 times Tn by 2 plus theta n if n greater than 1. So, this is the type of recurrences. So, how to solve such kind of references? So, for solving that recurrences, we have to use the above 4 method, that is substitution method, iteration method, recurrence tree method, and master method. Okay. So, first method I have taken substitution method. So, one example I have taken, that is the linear search. For linear search, we use the input array A and what element to be searched, that is element x, and the question is x belongs to A, that means that element belongs to an array or not. So, the idea behind linear search is to search the given element x linearly, that is sequentially in the given array. A recursive approach to linear search first search the given element in the first location. Okay. If not found, it recursively call the linear search with the modified array without the first element. Okay. The problem size reduces by 1 in subsequent calls. So, here the linear search we are using with the help of recursion. So, at the when we solve that linear search problem with the help of recursion, what will be the recurrence? So, let Tn be the number of comparison. Comparison means at each step you compare your element x to the given array element. Okay. If that element x found that an array, that will stops your recurrence. So, Tn be the number of comparison required for linear search on an array of size n. Noted that if element size, if array size is 1, that is the time complexity or number of comparison equal to 1. So, no comparison is required actually. So, what will be the recurrence when we have the n elements? So, Tn equal to 1 plus Tn minus 1, because if we say n is the number of comparison for n element, if we compare the first element with the element x, if it is not found, then we have a problem size, that is n minus 1. So, 1 plus Tn minus 1. Actually, in every step, in every recursive call, the problem size will be reduced from n minus 1 to n minus 2, n minus 2 to n minus 3, up to the problem size equal to 1. So, at every step, the number of comparison equal to 1. So, 1 plus 1 plus 1 up to the problem size equal to 1, that is T1. So, when we calculate that the time complexity, that is the number of comparison for linear search, that is Tn equal to how many ones are there, that is n minus 1 ones there, n minus 1, and when the problem size is 1, in that case there is no comparison actually. So, we can say 1. So, n minus 1 plus 1, that is 1 n. So, Tn equal to theta n. So, for linear search using the recurrence, that is Tn equal to Tn minus 1 plus 1, we get the time complexity is theta of n. But this is the case where we use the recurrence relation, recursive call, recursive approach. In simple, in iterative search also you can solve that linear search problem, that also take the theta n time. But here there will be extra space we involve, that is auxiliary space, that is the stack size, that is order of n. So, any problem, that is linear search problem, can be solved either in iterative way or recursive way. When we solve in recursive way, we can get that kind of recurrence, that is T n equal to 1 plus T n minus 1. In case of binary search, okay. So, binary search means what is the input? Sorted array A of size n and element x to be searched, okay, like in linear search. So, the question, same question is there, is x belongs to A or not. So, what will be the approach of binary search? Check whether A n by 2 equal to x, that is middle of the element present on the in the array, and that belongs to x or not. If that A n by 2 equal to x, if it is true, then it will return, okay. If x is greater than A n by 2, that means then prune the lower half of the array, otherwise prune the upper half of the array, okay. That means x, because in binary search the element are sorted in array, sorted array is given, but in case of linear search the element are not sorted, okay. So, when we found middle of the element, that middle of the element is matched with the element x or not. If x greater than A n by 2, that means no need to see the element which are greater than A n by 2. So, the pruning lower half of the array, otherwise pruning, if x is less than A n by 2, the pruning the upper half of the array. Therefore, pruning process happens at every iteration, and after each iteration the problem size, that is array size under consideration, reduced by half. That means earlier the problem size is n, and in the next iteration problem size is n by 2, and again in next iteration problem size is n by 2 square, that is n by 4. Similarly, we can reduce the problem size up to the problem size having 1 unit. So, what will be the recurrence relation for the binary search? That is T n equal to T n by 2 plus order of 1. Order of 1 means last step, okay. So, where T n is the time required for binary search in an array of size n, okay. So, after reducing the problem size at each iteration, we will get after the kth iteration T n equal to T n by 2 k power k plus 1 up to the k minus 1. So, since T n equal to 1, T n means the problem size is 1. So, at that case only one element is there. So, the number of comparison you can say that it will be constant. So, n by 2 k power k equal to 1, that is problem size is 1. So, in this case k equal to log n base 2, okay. So, this is the number of iteration, k means number of iteration. After kth iteration, what will be the time complexity? So, T n equal to n by 2 k power k equal to 1, that is T 1 plus k, k means number of iteration, how many times these iterations happen. So, 1 plus log n means log n simply. So, what will be the time complexity? That is log n base 2. So, this is required for the binary search, and this recurrence T n equal to T n by 2 plus order of 1 will give the result log n base 2. That recurrence can be solved using the substitution method, and in this case also we use that substitution method. In merge sort also, in merge sort the divide the array into two equal subarray and sort each subarray recursively and do the subdivision operation recursively till array size becomes 1, okay. So, all in binary search or merge search we use the divide and conquer principle. So, divide and conquer principle means if we have a problem size n, we divided by n by 2 or n by 4 or n by 8. That means recursively we have a problem size reduced to be half, and at last we have a problem size 1. So, what will be the recurrence relation for the merge sort? In binary search, at every step we prune the half of the element, but in merge sort, because we divide the problem in sub problems, and we have to carry all the sub problems in concur step. So, there is no need of pruning in this merge sort. So, T n equal to 2 T n by 2 plus n minus 1, and at every step the n by 2 every step the problem size become half. So, after putting the value of T n by 2, we can see 2 into T n by 2 square plus n by 2 plus n minus 1, and we after the kth iteration, what will be the value of kth iteration? So, n equal to 2 k power k, that means k equal to log n base 2. So, what will be the value of T n? T n equal to 2 k power k into T 1 plus n plus dot dot dot, and what will be the value? 2 to the power 0 up to 2 k power k minus 1. So, using the geometric expression, so a into r to the power n minus 1 divided by r minus 1. So, what will get, that is 2 k power k minus 1 and 2 k power k equal to n. So, n minus 1 and T n equal to 0, because there is no comparison required if n equal to 1. So, T n equal to n log n minus n plus 1, that means overall we can say n log n. So, this is the complexity of merge sort, and this recurrence T n equal to 2 T n by 2 plus n will be solved through the substitution method. So, recurrence relation using a change of variable technique, because in substitution method one important thing equal, because T n equal to 2 into T root n plus 1 and T n equal to 1. First, moving ahead, we have to use some substitution technique, so that this equation will come in certain form. So, after putting the value of n equal to 2 to the power m in the given recurrence, we can get t equal to 2 to the power t into 2 to the power m plus 2 into this, and finally, we get the t of t to the power m equal to 2 into t, and we introduce that t of 2 to the power m equal to s m, and we can get s m equal to 2 s m by 2 plus 1, and at that moment of time we can use the substitution after the substitution method, and after the kth step we can get s m equal to 2 to the power k, and what will be the value of k? So, k equal to log m base 2, and putting that value we can get the value of T n. So, finally, we can get the value of T n equal to theta log n. So, these are the substitution before substitution. This is the this method is substitution before substitution. Next is iteration method. So, iteration method, it means to expand the occurrences and express it to the summation of terms of n or initial conditions, that is T n equal to 1 if n equal to 1, or T into 2 to the power n minus 1 if n greater than 1. This is the problem, this is the recurrence. How to solve using the iteration method? Just put T n equal to T into 2 to the power n minus 1 and iteratively put the value of T n minus 1 again. So, if you put the value of T n minus 1, you can get 2 into T n minus 2, and after third step you can get the 2 to the power 4 T n minus 4, and repeat the procedure for ith times. That means, you can say the ith iteration. After ith iteration, what will be the value of T n? So, T n equal to 2 to the power I into T n minus I, and put that n minus I equal to 1, because after ith iteration the problem size will reduce to 1. So, I equal to n minus 1, and putting that value we can get 2 to the power n minus 1 into T 1, and T 1, that is if n equal to 1, T 1 value equal to 1, that will be 2 to the power n minus 1. This is the case you already know, the tower of Hanoi problem. In tower of Hanoi problem, if number of disk is increases, the value of T n equal to 2 to the power n minus 1, that is your exponential time complexity. Again, this is the second example of iteration method, that is T n equal to T n minus 1 plus 1 and T 1 equal to theta 1. So, in this case T n, if we put the value of T n minus 1 in the previous T n equal to T n minus 1, we can get the T n minus 2 plus 2, and again the value of T n minus 2 we will be putting T n minus 3, and after kth iteration you can see the value of T n equal to T n minus k, that is T n minus k equal to T 1, because the problem size will be reduced to 1, and if the problem size will reduce to 1, that will the time complexity is theta 1. So, putting that value T n minus k in the previous equation, that is T n equal to theta 1 plus n minus 1, because the k value equal to, if we put the k value equal to n minus 1 or T n minus k equal to 1, that is theta 1 plus n minus 1. So, overall calculating that value we get the theta n. So, this complexity resultant theta n. We studied about the iteration method and your substitution method. So, next is your recursion tree method. So, in this method a recurrence relation is converted into recursive trees. So, each node represent the cost incurred at various level of recursion, okay, and the total cost is determined by adding up the cost of all levels, okay, because in this recursion tree method we make a tree and each level we calculate the cost, and after adding all the levels cost of all level we can get the overall time complexity or overall space complexity also. So, what is the steps to solve recurrence using the recursion tree method? So, first draw the recursive tree for a given recurrence relation. Second, calculate the cost at each level and count the total number of levels also, because the number of levels into the cost of each level you can get the overall cost. So, the count the total number of nodes in the last level also and calculate the cost of last level. So, last level, that is your leaf node. So, number of leaf nodes and the cost of each leaf node will be counted and sum up the cost of all the levels in the recursive tree. Finally, we can get the result of recursion tree method. So, I have taken one example, T n equal to T n by 2 plus constant. So, using the recursion tree method, T n is further divided by T n by 2 plus T n by 2, okay, and again T n by 2 is divided by T n by 4 plus T n by 4. Similarly, so at each level what will be the cost? If T n, that is the number of input equal to n, so that cost will be C, that is you can write 2 to the power 0 into C, and n is divided, that is problem is divided into two part, n by 2 n by 2, and that cost, that is C, because at each level when the problem is divided into half, so the cost associated is C. So, n is divided 2 halves. So, 2 half means 2 C, C plus C, that is 2 C, and we can write 2 to the power 1 into C. Again n by 2 will be divided into 2 half, that is n by 4, and how many cost associated? Because at every n it will divided by n by 2, the cost associated is C. So, how many n by 4 is there? 4 n by 4 is there. So, 4 C's are there, 2 to the power 2 into C. So, we can see at each level the cost will be, at the root level the cost will be C, the next level is 2 to the power 2 into C, and the next step is count the total number of nodes at last level and calculate the cost of last level. So, here you can see the problem size is reduced by n by 2 to the power 0, n by 2 to the power 1, n by 2 to the power 2, n by. So, this is the longest leaf node. Okay. So, size of problem at last level, that is n by 2 to the power k, when we assume that will end after the kth iteration. So, n by 2 to the power k equal to 1, that is k equal to log n, that this log n is number of levels. So, total number of levels in recursive tree equal to k plus 1 including the root node. So, log n base 2 plus 1, that means total number of level is log n, and number of nodes at level 0, how many nodes are there? So, level 0 nodes are 1, level 1 nodes are 2. Similarly, the number of nodes at level k, because how many levels are there? K level. So, log n base 2. So, that will be the what will be the cost? 2 to the power log n base 2, that value will be n. Okay. So, cost of sub problem at each level, that is level kth level, that is last level, will be n into T1, that is n into 1, that is n. Sum of the cost of all the level, because how many levels are there? Log n level are there, and this step 3 give the cost of last level cost, that is n. So, every step, that is Tn at the level 0 C, level 1 2 C. So, we have to calculate all the cost at all the level, number of levels minus 1 times into last level. What is the cost of last level? We calculated in step 3, that is theta n, and the number of levels is log n base 2. So, 1 plus 2 plus 4, if we get the common C, we get the value of 1 plus 2 plus 4, that is log n times. This is your geometric progression series, and we solve that geometric progression, we can get the n value, and that is n plus theta n, that is overall n. So, overall time complexity is theta n. So, at last that is the fourth approach to solving any recurrence, that is the master theorem. First we have to know where to use it, where to use, what is the actual form of master theorem. So, the master theorem is used for solving the following type of recurrences. We cannot use that method to anywhere. We have to think about this, the standard form T n equal to A into T n by B plus F n, where A must be greater than equal to 1 and B also must be greater than equal to 1, and the constant, that is F n, be a function and can be interpreted as, let T n be defined as the non-negative integer by the recurrence. In the function, to the analysis of recursive algorithm, the constant and function takes the following significance. N is the size of problem, where in this equation T n equal to A T n by B plus F n, n is the size of problem. A is the number of sub problem. When we divide that problem, like we in merge sort or in binary search, we divide the problem. In merge sort, we divide the problem in 2 halves. Okay. So, that is why we have written in recurrence 2 into n by 2. So, A is the number of sub problem in the recursion, n by b is the size of sub problem, because in merge sort, the example of merge sort, when we write 2 into T n by 2, that means each sub problem have size n by 2 and number of sub problems is, that is A, that is 2. So, in merge sort, every sub problem size n by 2 and the number of sub problem is 2. 2 into T n by 2 means, and F n is the sum of the work done outside the recursive call. When we, like in earlier example also, when we produce like C, like in this example, when we produce T n equal to T n by 2 plus C, that means after conversion, after recursive call T n equal to T n by 2, the cost associated is C. So, F n is the sum of the work done outside the recursive call, which include the sum of dividing the problem or sum of combining the solution to the sub problem, like in divide and conquer approach. So, F n is the work done, you can say simply. So, these are the cases of master theorem. So, master theorem, this is the standard form, let A must be greater than equal to 1 and B must be greater than equal to 1, be constant, and F n be the non-negative function, that is your positive function, and T n equal to A T n by B plus F n. So, these are the cases, case 1, 2, 3, and these cases can be understand like when F n equal to big O of log n base B, and the F n equal to theta of log n n to the power log A base B. So, all these cases will be make you understand through the examples, like in first example master theorem, T n equal to 9 into T n by 3 plus n. In this case, we have to calculate, we have to think about the value of A and B. What is the value of A in this equation? A equal to 9, B equal to 3 and the F n equal to n. So, first we have to calculate n to the power log A base B. So, n to the power log A base B, A equal to 9 and B equal to 3. So, 9 base 3, that is 2. So, n square, this value is n to the power log A base B, and what is the value of F n? F n equal to n. So, you have to comparison, you have to compare the n to the power log A base B and F n. So, which one is greater? N square is greater or n square is greater. So, obviously, the big O of n square and n is n square. So, this is the first case of master theorem. What is the first case? F n equal to big O of n to the power log A base B for some constant epsilon greater than 0, and what will be the T n time complexity? Theta of log n n to the power log A base B. So, in this case, what will be the time complexity? Because n to the power log A base B, that is n square, is greater than n. So, theta of n and n square, that is n square. So, this satisfies the master theorem case 1. Example 2, in this case again we have to, at every time if we get the format T n equal to A T n by B plus F n, at every time you calculate the value of A, B and n to the power log A base B. When n to the power log A base B, A value equal to 1, B value equal to 3 by 2. So, log of 1 at any base, the value will be 0. So, n to the power 0, that is 1, and that is equal to F n. Okay. N here n to the power log A base B and F n both are same. So, in case of both n to the power log A base B and F n are equal. So, what will be the case? That is the second case, that is second case F n equal to theta of log n base B. So, in this case T n equal to theta of n to the power log A base B into log n. So, what will be the value of n to the power log A base B? That is n to the power log a base b, that is 1. So, 1 into log n, that is log n. So, final time complexity is log n. Example 3. In this case also we can get a equal to 2, b equal to 2. So, n to the power log a base b, log a base b means the value is n, and this is also equal to f n. So, this is also the case 2. So, n to the power log a base b and f n both have the same value. So, what will be the time complexity? So, T n equal to theta of n to the power log a base b into log n, and what is the value of n to the power log a base b? That is n. So, n into log n, this is the final complexity. And the last, that is the master theorem, example 4. Here again we calculate the value of n to the power log a base b, that is 3 base 4, and f n equal to n log n. So, comparing n to the power log a base b and f n, this is the case of master theorem third. F n equal to, that is omega n to the power log a base b for some constant epsilon greater than 0, and a into f n by b is less than equal to c time f n for some constant c less than 1. So, in this case T n equal to theta of f n. So, in this example you can check this satisfy the case 3, and you just multiply a into f n by b. What is the value of a into f n by b? That is 3 into f n by b means n by 4, 3 into n by 4 into log n by 4 is less than c into n log n. So, in this case what will be the value of T n? So, T n equal to theta of f n. F n means n log n. So, if we compare f n with the n log a base b, so n to the power log 3 base 4 is the smaller value, and f n have a greater value, that is n log n. So, n log n will be the final result, because we take the average value, theta means average value. So, n log n will be the answer. So, next is example, T n equal to 4 T n by 2 plus n square log n. Again we have to calculate n to the power log a base b, and after calculating, what will be the value of n to the power log a base b, that is n square, and what will be the value of f n, that is n square log n. If we compare the f n and n to the power log a base b, here the n square, here the n square log n. So, here the case 3 states that f n should be polynomial larger, but here it is asymptotically larger than n to the power log a, because in this case n to the power log a base b, that is n square, and f n equal to n square log n. So, this is asymptotically larger, not the polynomially larger. So, if recurrence relation fail into the gap between the case 1 and case 2, or case 2 and case 3, master theorem cannot be applied. Such recurrences can be solved using the recursion tree method. Okay. In last example, in this example, this will be greater than like polynomial time, not the asymptotically larger. So, in case of asymptotically larger, we have to calculate through the recurrence tree method. So, this is all about your recurrences. So, after getting if I am going to summarize these things, first we get the recurrences, and after getting the recurrences you have the 4 methods in your syllabus. First you use the substitution method, then iteration method, then recursion tree method, and finally master theorem. But in case of MCQ question, you can use directly master theorem, and this is the simple fundamental of master theorem. Just compare the value of a and b, that is T n equal to a T n by b plus f n, calculate n to the power log a base b and f n. If you compare which one is greater, if the n to the power log a base b greater, then T n equal to theta of n to the power log a base b. If f n is greater, then T n equal to theta of f n. This is the overall recurrences, solving the recurrences. So, thank you so much.